Yep, comes on everyone. The last thing we did was this, the weird rope. Next thing, springs. So we dealt with normal reactions and tensions. Third force is the spring force. So what are springs? So springs, they oppose deformation. Again, what is deformation? Compression or elongation. So springs don't like to get elongated or get compressed. So they generate restoring forces. Which is proportional to elongation or compression. So this is how we represent a spring. This we call as a natural length. Natural length meaning there is no elongation or compression. Spring is fine with this. This is the position the spring wants to be. Now see what happens. If you try to pull the spring, this is the elongation. The spring will pull you back. If you compress the spring, so X will be this way, the displacement, the force will be forward. So this is what I was saying. The spring will always oppose your motion. If you try to pull it, it'll pull you back. If you try to push it, it'll push you back. So here X is your elongation. Here X is your compression. So this force is given by F spring is given by minus K X bar. This is the formula there. The negative sign indicates opposition. Look at there, F and X are always opposite. If you pull it, the force is backward. If you push it, the force is forward. The negative sign indicates opposition, and this K is called spring constant. What is the physical significance of spring constant? Higher the value of K, stronger the spring. So if you can see, K is nothing but force per unit deformation. So if the K value is large, that means even for a small deformation, you get a huge force. So the physical significance is higher the K, stronger the spring, or more difficult to deform. So this K value depends on the material and also depends on the dimensions. We will deal with that in another chapter. So regarding K, we'll not talk much about it right now. There, have a look at this. Clear, everyone? Then we have something called combination of springs. First thing, series. So two springs are in series if they have same tension and in the same branch. They should have same tension and they should be on the same here. K1, K2. We can replace this both the springs with one single spring of K equivalent, where K equivalent is given by 1 by K equivalent is 1 by K1 plus 1 by K2. This is opposite of resistors. So if this spring is X1, this spring is X2, this spring will be X1 plus X2, where X1, X2 are elongations. Since all have same tension, K1, X1 must be equal to K2, X2 is equal to K equivalent into X1 plus X2. So from that we can derive this. But this is the main idea there. If you have two springs in series, you can replace it with one single spring, which is given by 1 by K equivalent is 1 by K1 plus 1 by K2. This will be reverse of the resistors. When they're in parallel, they will have same elongation. You can replace this with one spring, K equivalent, where K equivalent is K1 plus K2. They'll just add up. So be careful there. The formulas will be reversed like resistors ka reverse hai.
Sir,
हाँ प्रतीक.
sir, where you have written 1 upon K equivalent का formula, just below
हाँ,
that, K1 X1 plus K2 X2, right? Or will it be equal?
that is the equal to it. All have same tension.
Okay, tension.
That has nothing to do with this. That's a different formula.
Okay.
That's the tension in the springs. This must be same. Clear this? Then there is something even better than this. What happens if you cut a spring? Now, when you have a spring like this, the spring constant K is actually given by YA by L, where A is this area of cross section, meaning how thick the spring is. It depends on the thickness of the wire that you're using and length of the spring. This Y is called an Young's modulus, which tells you how strong the material is. We'll deal with that in a different chapter. So Y is the strength of the material. For example, if you make a spring with a steel wire versus a copper wire, steel ka Y is more than copper. Or let's say plastic spring is even better. Plastic is much weaker. Now, when you cut a spring, what remains constant? Y won't change, right? When you cut it, material won't change. And when you cut it, the area won't change. Just give me a minute. What happened to this light? So when you're cutting it, K into L, YA will remain constant. Because whenever you're cutting something, material won't change and area won't change. So we get K into L is constant. So pretty good result. So let me show an example. That means if you take a spring, let's say length is K and L, and if you take this thing and cut it into two pieces of L1 and L2, you will get two springs. This will be K1, L1, this will be K2, L2. You can be sure K1, L1 will be equal to K2, L2 will be equal to capital K into L. That product will always remain constant. Example, let's say we have a spring K and L. Let's say you cut this in the ratio of L by 3 and 2L by 3. So you will get two springs. So that small spring will be L by 3. Iska spring constant should be 3K. Let's take it as K1. The bigger spring ka length will be 2L by 3. Let's call it K2. Now from the formula, K1 into L by 3 must be equal to K into L. So K1 will be 3K. So whenever you cut a spring, the spring constant actually becomes bigger. K2 into 2L by 3 must be equal to K into L. K2 is 3L, 3K by 2. So cutting a spring changes the spring constant. So be careful with that. Spring constant depends on the how much length you have. Meaning the reason is this. Think of like this. If you have, imagine if you have like this 100 coils. If I pull the spring by 100 centimeter, means each coil stretched by 1 centimeter. But if I have only 10 coils and if I stretch by 100 centimeter, means each one stretched by 10 centimeters. You're getting it? So there's much more deformation. The material got more stretched, so they'll apply more force. So smaller springs are stronger than longer springs. Have a look at this. So these are the results you need to remember. Quite a useful one. We are going to encounter these things again in a chapter, called simple harmonic motion. Then we are going to encounter this again. Combination of springs. So do have a look at this. Clear? Next thing, let's see a question. We have a spring here, we have a block here. Let's say this is 2 kg. We have one more spring here. This is 3 kg. Let's say the spring constant K1 is 200 Newton per meter. This is 300 Newton per meter. Find the elongation in the springs. System is at rest. Okay. Remember, steps are same. Draw a free body diagram and check it out. Let's see. First thing, let's draw the FBT for the 2 kg block. What are the forces? Now let the spring be x1 on the top. So springs will understand one thing. The spring is pulled, then it will pull you back. So the upper spring will pull with k1 x1. You have your own weight 20, and the lower spring will pull with k2 x2. And if you draw the 3 kg block, this will be k2 x2. This is the weight 30. Does this make sense? So that k2 spring will pull 3 kg up and will pull 2 kg down. Everything is in equilibrium. So k2 x2 will be 300 into x2 is equal to 30. So we get x2 is equal to 1 by 10 meters or 10 centimeters. And this guy, k1 x1 will be k2 x2 plus 20. But I know k2 x2 is nothing but 30. So this is actually 50. So 200 into x1 is 50. So x1 is equal to 1/4 meter or 25 centimeters. Easy, straightforward. So that's what you have to see. Is the spring elongated or compressed? If it is elongated, it will pull you. If it is compressed, it will push you. Clear? Turn in the page. All clear with this? Great. So we have 6 springs like this: KK, 2K, 2K, 3K, 3K, and 3K. Initially, all are in natural length. So when released slowly, means you're holding the block and slowly leaving it. The block moves down and stops. Find a distance moved by the block, and let's call this point as A here. Let's call this point as B here. Find distance moved by the block and A and B. So initially all are in natural length. When you leave it, this will aram se come down. Find the distance moved by the block. Find the distance moved by the point A. Find the distance moved by the point B. Where should the block? Yeah, the block moves down. ठीक है ना? Is that the most important thing today? Solve the question. Distance moved by the block is 49 mg by 36k. Okay. I think two people got the same answer. Ansh, Surya, both of you got the same. What about A and B? Those are the interesting ones. Someone got 17 by 12, which is so what we do? So these ones are the red ones. So I can replace 3k, 3k. All three are in parallel. When they're in parallel, you can add them up. So we will get one spring here. This will be 9k. 2k, 2k are in parallel. They'll add up. That would be 4k. And that last one is k. So if you take the equivalent spring, 1 by k equivalent is 1 by k plus 1 by 4k plus 1 by 9k. How much is this? 5 by 4 plus 1 by 9, 9, 5, 45, 49 by 36. So this would be 36 by 49k. That is your k equivalent. So you can replace this whole thing with one spring. K equivalent. So the block will behave as if k equivalent into x mg. We get x is equal to 49 mg by 36k. That is the distance moved by the block. What about A and B? Now I try to understand here, where is A and B? B is this point, A is this point. Since all are in series, tension will be same. Agreed? Since all are in series, tension is same. And how much is the tension? Which is mg. Tension is nothing but mg by the block. Agreed? Now let's say this upper spring stretched by x1, the lower spring stretched by x2, this thing stretched by x3. So let 9k stretch by x1. So how much will that be? 9k into x1 must be equal to tension, which is equal to mg. So x1 is equal to mg by 9k. Similarly, 4k into x2 must be equal to mg. Therefore, x2 is equal to mg by 4k. Now you tell me, whatever amount this spring stretches, isn't that the distance traveled by b? Whatever the spring stretches on the top, isn't that the distance traveled by b? Similarly, whatever elongation 9k and 4k will stretch, isn't that the distance traveled by a? Is that making sense, everyone? If the 9k spring stretches by 1 centimeter, meaning the spring will become like this, matlab B will go here, right? So the distance moved by B is nothing but elongation in 9k. Distance moved by A is nothing but elongation in 9k plus 4k. I hope is that making sense? Distance by moved by B is elongation in 9k. Whatever that 9k spring goes, you'll have the same thing, which is mg by 9k. Similarly, distance moved by A is elongation in 9k and 4k, which is x1 plus x2. mg by 9k plus mg by 4k. Can we take A and B as two blocks? A and B as two blocks? I don't know what you mean by that. You can tie. It will work. It's the same thing. It doesn't make any difference if you put M0. Try and see. If you're getting the same answer, then it is fine. It should work. But unnecessary, right? Try to get the basic logic there. Meaning whatever this point B goes, that is because of 9K. Whatever A goes is because of 9K, 4K. Whatever is the block goes because of all three of them. Is this making sense, everyone? That would be a good question. What is the distance moved by B or A? Do check. Clear? Next one. Any doubts on this? Clear now, Ojus? Jainil? Daksha? Clear? We have a wall here. We have a spring balance. 10 kg block. Ten kg block and 10 kg block. There's a 10 kg block, 5 kg block. This is S1, this is spring 2. This is 10 kg and 5 kg. Now, what does the spring balance measure? Remember, just like weighing machine, spring balance measures tension. It measures the tension in the string and shows what it measures, and what it shows is different, and shows the reading tension by G. So it will measure whatever tension is there and divide by G, and it will show that as a value. Just like a weighing machine measures normal reaction divides by G. So here this thing measures tension by G. So all four cases, find the reading of the spring balance. What does the spring balancer show in all these cases? Spring balancers simply measure the tension in the string and divide by that and finish it off. Let's get them. Be careful with the second one. Forgot the horse ka story kya? Just because two people are pulling doesn't mean you'll get double. Try. I'll give you 1 or 2 minutes more, then I'll show you. D is a good one out of all. If I had to ask in the exam, I'll either ask you D or B. Let's see. Don't forget, how do you find tension? Find the FBD tension T. This would be 100. So tension is 100. So reading will be T by G, 10 kg. Here, what is the tension? System is in equilibrium, 100. So what will be the reading? 10 kg. Just because you kept two blocks, it doesn't mean anything. Remember that Horskov story? This one and this one are identical problems, isn't it? The wall is also pulling with the same force. What about this guy? So this guy, this tension here, T2, this will be 50. So T2 will be 50 newtons. So the reading of the spring S2 will be 5 kg. Whereas this tension T1 here will balance all the blocks. So T1 will be 150 newtons. So S1 ka reading will be 15 kg. Make sense? I hope this was easy. You just need to find the tension. Everything were at rest. And we have already done this A and B ka problem. This was at a Horskov thing which we did. What about D? Now D, my system is not at rest. It's moving. What is the reading of the spring balance? Hmm. Hmm. Let's see वो just that looks right, but देखना पड़ेगा. Twenty by 3. D is not 5 kg. Purvaja, I think you're right. Abhinav, you're wrong. Like I said, what you need to find? You need to find tension, right? What to do? Step 1, choose your system, draw the FBD. Tension. This would be 100. Let this be acceleration. This would be tension. This would be 50. This is the acceleration. Remember, springs are massless, so it is the same string literally. Write the forces equation. This would be T minus 100 is equal to 10 into minus A. This would be T minus 50 is equal to 5 into acceleration A. Take T from here and dump it there. So 50. What you want to find is this thing, right? I can divide them. T minus 50 by T minus 100 would be 5A by minus 10A. That would be minus half. Cross multiply. 2T minus 100 is equal to minus T plus 100. We get 3T is equal to 200. So tension will be 200 by 3 newtons. The reading will be tension by G. That's 20 by 3 kgs. That's what the weighing machine thinks, the spring balance thinks. Spring balance doesn't care what weight you keep. What is the tension divided by G? Is this clear, everyone? So be careful. That's what spring balancers do. They don't measure weight, they measure tension. And they show you something else. See part here.
Yes, sir. Done. Thank you.
Clear with this? Next one. This is a good one. If I had to ask you in advance, I'll ask you this question. We have a spring. Right? Spring ka thing is K and length L. Now what you did, somewhere in the middle here, point A, you connected a small rod. You welded a rod there, and then you started applying force F. Are you getting what you did? So you're catching at the center of the spring somewhere, and then you're pulling it. Is that making sense? What you're doing? You're not pulling at the corner. You're not pulling there. You're catching somewhere in the middle, and you're pulling it. So you're pulling at this distance here. This is 0.2 L, and this is 0.8 L. So you kept some kind of rod or something, and you're pulling that. Set point A on the spring, a force F is applied. Right. So the question is, find the distance moved by A in equilibrium. How much will that point A move? Think it's a good one. Is the question clear? You're not holding at the corners. You're caught it in the center somewhere at 0.2 L, and then you pull that part to the right. What makes this question different is the right part of the spring will get compressed, isn't it? The left part of the spring will get elongated. So some part of the spring is compressed, some part of the spring is elongated. So this is not a regular one. So how do you do this thing? Try. It's a good one. नहीं वो just life is not that easy. I need to get a new light here. Too dark. Hmm. नहीं पूर्वजा. Let's see. So the catch here is, since the left part and right part are behaving little differently, cut them. You treat them as two different springs. So I have one spring of 0.8 L and I have another spring of 0.2 L. Let the spring constant be K1. So the moment you're cutting it, spring constants will change. The right part is compressed. And the left part is elongated. And from that formula, we know K into L is constant. So this spring will be K1 into 0.8 L is equal to KL So K1 would be 5K by 4. This thing is K2 into 0.2L is equal to KL. K2 will be 5K. So this whole thing behaves as if we have a spring here, 5K by 4. You can just imagine this point A, another spring of 5K. Now, when you apply force F, let's say this thing moved by distance X. There is a question, right? Find how much it moved. That means the right part will get compressed. So if you draw the FBD here, the right one it got compressed. So it will push you with a force of 5kx. The left part got elongated. It will pull you with a force of 5kx by 4. Agreed? This will pull. This will push because it got compressed. And the force applied is F. So this system should be in equilibrium. Therefore, F is equal to 5kx plus 5kx by 4. This would be 4F by 25k. That's your distance moved by the point. Check. Right, Ojas, you got that. Is this clear, everyone? You cannot treat this as a single spring anymore. Because till now, the reason, see, you can treat one thing as a spring if the entire thing is behaving identically. Here, half the spring is compressed, half the spring is elongated. They are behaving quite weird, so just cut it there and treat them as two parts. Is this clear? Because normally all the questions, right, we apply forces on the end of the springs. But if we do something in the middle, this is what will happen to the question. Do have a look at this. Ask me if you're confused. Clear, everyone? Next one. Next thing. Now springs, right, they behave little differently like till now what we have seen. So there's a bit of a theory. That is the reason we kept it in the end. They're not tough, but they have a little different behavior. So most of the cases, right, we study ideal springs, which are massless. So in all our portion, we have massless springs. Rarely we'll encounter spring with mass. Let's see how they behave. If you take a massless spring, now real world they don't exist. When you say a massless spring, we'll take a spring with very light weight. So if you have a block connected to a spring, okay? So when a massless spring is cut, it immediately comes to natural length. Meaning, if you just cut it somewhere here, let's say you cut it here, doesn't matter actually, we'll cut it here. The moment you cut, the spring will come to the natural length and the block will just get disconnected. Why does that happen? Reason, if you take force is equal to ma, right? And since it's a massless spring, m is 0. Since m tends to 0, acceleration will tend to infinity. So the moment you cut, the body will have an infinite acceleration. This block will just fall with gravity g, and the spring immediately moves to the natural length. Is that making sense? You don't need time. When you have infinite acceleration, you don't need time. Instantaneously it will move. Matlab, even in a 0 time, the spring will go back to the natural length. This is how a massless spring would behave. Clear with this? So the moment you cut it, there is no tension in the spring anymore. So force becomes zero immediately. Let's say this was the natural length initially. So initially it was elongated by some amount x. So the moment you cut that spring, it will travel distance x in zero time because you have infinite acceleration. So simply remember this thing. If you cut a massless spring, it will come to the natural length immediately. नहीं, यहाँ पे time negligible नहीं है, zero time है because you have infinite acceleration. Like I said, infinity doesn't make sense. But what if the spring has mass? Look at this thing. This questions we will not solve, but they can ask us theoretical questions. If you have a spring with mass, it behaves slightly differently. It takes time. So when a spring is cut, it takes time for spring to come to natural length. That is, spring force is not zero immediately. It will become zero, but not immediately. So it does something like this. So if you take a block here, if you put a block M here, and let's say this was your natural length, it got stretched a bit. Now, if you take a scissor and cut it here, right? If you wait for a little time, this is what you'll notice. Let's say the block is here. You will notice the block is still here. The spring is coming down. Then after some time, the block is still here. The spring is coming down. The block won't move. The block will remain at the same position. Then once this thing comes here, at this point, so here the block acceleration is zero. Block acceleration is zero. Now this guy will start moving. Now you have come to the natural length, meaning now the force becomes zero. Then the block will start moving. So block will not move until the spring reaches the natural length. Inertia, basically. The reason why this is taking time is because same logic. Acceleration will be forced by m. M is not zero now. This is a finite value. This is not infinity. The time will be very small, but it is there. Are you getting the difference between a spring with mass and without mass? So from here to here, there is a small time delay in microseconds or maybe milliseconds. But if it is a massless spring, there's no one to stop you. You will just rush through and you're done. But if you have little mass, springs with mass, they will take time. Let's see how would that look like. Look at this thing. That's a big spring from the top. I don't know. Previous one, could you see that? Actually, in a slow motion, you can see this thing. See, when he's leaving, that is a slinky. Okay. Now see, he leaves at the top. Observe the bottom. The bottom doesn't move. दिख रहे? The bottom will move when this comes to the natural length. Now it starts moving. Look at this thing. This is a bigger one. You can see this thing in more better. See, as the top one is falling, the bottom one doesn't know what is happening at the top. It takes time. See, this that is getting compressed. The bottom part is still there. And now it moves. This is what I was saying. If you have mass, this is what would happen actually. So the massless case is an exception. This is another same thing from the bottom. You can see it is literally at rest. What is happening, right? The part which is just above this is still elongated. So those things are applying force. They won't know that the spring came to natural length until the upper part comes down. So there is a delay. This is what we call as inertia. The system doesn't know what happened. It takes time. Now it moves.
So this is the modelling that I've been doing, and so this was done with the purpose of trying to.
Is that clear, everyone? That is the difference between a massless spring and a spring with mass. Clear? Next thing. Any doubts on this? What is the difference between a string and a spring? Now, generally, until unless mentioned, we'll always take massless springs. So keep that in mind. We always assume massless springs until something is measured. They should mention it. At least in the problem solving. You can't do with, if springs are mass, you can't solve it. It's not that easy. So this is one concept of the springs. How do springs behave when you cut them? The second concept is, what is the difference between a string and a spring? This is important. So when you take a string and a spring, when you cut them, tension in the springs, not meaning not cutting, but tension in the strings can change instantaneously. And whereas in springs, it takes time. I'll show you what it means. We're not cutting here. If you cut it will change immediately, but we're not cutting anything here. Let's see how does that change. For example, see, if you put a block here, mass M, let's say there is a hook here. You take another block M here with a hook and you're trying to attach it here. Now, initially, the string tension T, this is mg. So if you ask what is the tension, it will be T is equal to mg. The moment you keep the block to the hook, the strings cannot stretch. So suddenly, right, the tension T dash would be 2 mg. This is what I mean by tension can change suddenly. The moment you attach the block, tension will suddenly become double here. Suppose you can just unmute and ask. Matlab, it's a waste of time for you and me. I don't know why you do that. You write big stories. Just ask now. What do you want to ask? Bolo.
I was saying that if I cut it right where it is connected to the block, then
Here,
and it
this
is still
part,
connected to the rigid support.
same thing. Now, when you cut it here, block will fall down, but this spring will take time to reach there. It will go there. It will go here. Then it will come to the natural length.
So unlike the one that is we are cutting from the rigid support completely, it will take time to come
Go to the
back to its
natural length.
natural position. Then
Yeah.
it will start falling. Instead, if
यहाँ पे तो it will
block
just here the block will start falling immediately. Connection ही नहीं है ना. Yeah.
okay,
There's no connection. Who is stopping the block?
okay, yeah, that's what I
हाँ.
wanted.
बस इतना ही था. That whole story by the time I read only I'll get confused. चलेगा. Then so here T dash and mg, you can see here tension suddenly changes. So if you try to put some weight or something, strings will suddenly absorb the tension. Because strings are rigid, they cannot stretch, they don't have an option. But if you try to do the same thing with a spring, let's say you have a spring and a block M, K, and you have a hook here and you try to put a block. So initially this would be Kx, this would be Mg. We have x is equal to Mg by K. Now, if you put a block suddenly, now the spring doesn't know, it will take time for the spring to stretch. The elongation is still the same. Elongation cannot suddenly change. So spring force will still be Kx is equal to Mg. So this guy will apply Kx and this total weight will be 2 Mg. So this whole system will accelerate downward. So spring force depends on elongation, which is K into X. So the moment you attach the block, what is the elongation? Isn't it the same? If you give some more time, then these blocks will come down and then the spring will stretch. Spring will simply say, boss, my elongation is Mg by K. So it is still the same. So I'll apply this still the same force. So spring force depends on elongation or compression. So when you attach a block like this suddenly, right, spring force can't change. Right, given some time, the blocks will move. And then the force will change. The difference is that the spring force is K into X. If X is not changing, force will remain same. This is what I was saying. We're not cutting anyone here. We're just adding more blocks. So if you add a block to the tension, suddenly it will become tight. If you add a block to the spring, spring doesn't care. Spring will still say, I'm going to exert the same force at that instant. Is this making sense to everyone? So these are the two major concepts in a spring. If you cut a spring, it will come to natural length. If you add a weight to the spring, spring doesn't bother about it. Spring will still exert the same force. Because you need to give some time for the block to go down, the spring will elongate, and then you'll get the new force. Because F is Kx. Tension doesn't have anything like that. Because tension cannot stretch, it is rigid. The moment you add a block, tension will suddenly change. Is this making sense, everyone? So springs do these kind of all nonsense. So that is the reason we had to keep it in the end and we are studying it separately. You never had a problem with normal reactions and tensions. Clear, Ojas? Vignajit? Nikhil? Surya? Clear? Abhinav? Arya? Arnav? Ansh? Any doubts on the spring part? Jainil, Ishana, Pratik? All clear? Let's see a question. We have a block here, M. We have a block here, 2M. This is point A, this is point B. Initially, system is at rest. So there are two questions, okay? Find the acceleration of the blocks when spring is cut at case 1, you're cutting at A. These are two different questions. You're not cutting both at the same time. So if you're cutting only at A, what is the acceleration of the blocks? Second question, if you're cutting only at B, then what is the acceleration of the blocks? Two different questions. Let's do for the A part first. So if you're cutting the spring here, what is the acceleration of M into M? All springs are massless. Nothing is mentioned, so assume it is massless. I just taught you the springs with the mass just for the theoretical thing. So don't get confused. Because mains and advancement, you won't be able to argue with them. Take a minute, then I'll show you how to do one. Let me write you the steps, okay? Okay, so the idea here is, listen to this thing. Whenever you have spring problems, step 1, this is what we do. Find tensions in the spring before cutting. So the idea here is, the moment you suddenly cut something, the springs will take time to change. So first find tension in the springs before cutting. Then step 2, whichever spring you cut, uska tension 0 ho jayega. The spring which is cut has 0 tension. That's what we studied. If you cut a spring, tension will become 0 instantaneously. And the other springs are unaffected. The other springs don't care. The other springs are not affected. So that is the main idea there. Whichever spring you're cutting, only that will be 0, remaining will remain as it is. Then step 3, apply F is equal to MA. And solve, you'll get the answers. So let's see the first part. So step 1, before cutting, find the tensions. So this is M and 2M. So this tension, let's call it T2, which will be 2 mg, because this guy is balancing the 2 mg weight. This guy will be T1, which is 3 mg, because it is holding both the blocks. Agreed? The first part we are doing, you're cutting at A. You're cutting at A. So the moment you cut at A, the diagram, right, will look like, so M ka FBD, if you draw, tension at A, your own weight mg, this is T2. We'll do one thing, wait, let's call me, this is TA and TB, better. Now TA became 0 because you cut the string. Fair enough? The remaining two tensions are still there, and TB is unaffected, so that will remain 2 mg. This block will have an acceleration A, let's call it A1. So we have 2 mg plus mg is equal to ma1. A1 will be 3g. So this guy will go with 3g down. What about 2m block? If I draw the 2m FBD, this will be TB, this will be 2 mg, but I already know TB is still 2 mg. So this guy acceleration A2 will be 0. Is this making sense, everyone? So if you're going to cut at A, the M will get dragged down, 2M will remain at rest because the 2M doesn't know what happened at the top. Until unless the M comes down, 2M will not react, and it will take time to move, isn't it? So we are just finding all this thing at the instant, instantaneously. At the instant, we are not giving any time. B part, now when you cut at the B part, again, same thing, draw the FBD. So block A, there's a tension A, there is a tension B, there is your own mg. Now TA is unaffected, so it will exert 3 mg, TB becomes 0. That is the idea there. Acceleration, so 3 mg minus mg is equal to ma1. So a1 will be equal to 2g, so this guy goes up. For the 2m block, meaning you just draw the regular 4 FBDs, there's nothing different. TB, 2 mg, the only difference is, TB has become 0. This is the acceleration. 2 mg is equal to 2ma2. So this will just do a free fall. Please check your answers. Ask me, anyone not convinced with any particular step here? Keep the process simple. Find the tension before cutting. After cutting, whichever is cut, that will become 0, others will remain same. Draw the new FBDs. Put the forces, acceleration. I hope the idea is clear, everyone. So, keep it as clear as possible, because what happens, you might get the answer. You're doing it a little randomly without a proper process. Exam may, in that tension, you won't get ideas. So most people think, okay, if I'm getting an answer, what is the problem, even if it is a little clumsy? You need to ask yourself, in the exam, when you're under so much tension and pressure, will you be able to replicate it confidently? That is the whole thing. If you see everything that I teach you, right, I try to put steps. If you see this thing, these are the process. This is the process. So in case you go to the exam, you are scared, you got blanked out, answers will still come. That is how you should prepare. You can't stop yourself from getting tensed in the exam. So the more, systematically you prepare, exam may write, even if you're scared, you'll still do the problem. It's like, even when you're not well, or even when you're in a hurry, you still brush the same way. Isn't it? The process of brushing will not change because you're doing it every day. It becomes systematic to you. Itna doubt hai na? Try to brush with left hand tomorrow and see. You'll understand how different and weird it feels. The right hand, you won't even think. You're just brushing and thinking about everything. Try with the left hand, you will be like gone. Next one. All clear with this? Let's see one more like this. This is point A. This is point B. This is point C. 3 parts are there. This will take care of everything. Find acceleration to the blocks when you're cutting at ABC. 3 different problems. The process is still the same. Give it a try. Just get some water and come. Let's see. Step 1, find the tensions. So look at this thing here. So tension Tc would be 3 mg. Tension Tb would be 5 mg. Agreed? I need to find only the springs. The strings are anyway useless. So the first part, you're cutting at A. The moment you cut at A, now see what happens. Now remember, this is a string, okay? This is not a spring. So tension in the string will become suddenly 0. If you cut at A, tension A becomes 0. Tb will remain same. Tc will remain same. That is the idea there. Draw the FBDs. So M ka FBD. This will be Tb because that entire upper string is the same one. Huh? This entire thing will have the same tension. So that will be Tb only. Because the spring is connected to the string, tension will remain same in that. So that will be Tb, your own weight mg. This is Ta. But Ta became 0. This is your acceleration A1 and Tb is 5 mg. Net force 5 mg minus mg is equal to Ma1. A1 will be 4g. So this guy will just fly off with 4g. Then take 2m FBD. This will be Tb, which is 5 mg. Your own weight 2 mg. The Sika spring is pulling you down, which is also 3 mg. So 2m doesn't know what happened. Acceleration of 2m is 0. Similarly for 3m, tension is Tc. Your own weight 3 mg, but Tc is also 3 mg. This acceleration is also 0. The moment you cut A, B and the 2m and 3m don't know what happened. They will just remain there. This block A will fly off with 4g. Is this making sense, everyone? If you're cutting the string at A, string cut tension will be 0. Remaining two springs don't care what is happening. So the entire right-hand side, if you observe, the forces will look similar before and after cutting. So 2m and 3m won't even react. Sure how I did this? Now, can you try for B and C? Try. If I cut it B, what happens? Now you have to be careful. Spring cut tensions will remain same. Strings now can change anything. So you have no idea how will that string behave. Take a minute, give it a try, then I'll show you. That's what this question is good. This will take care of everything. Let's see. Now you're cutting at B. Now listen carefully. The game is little different here. So when you're cutting at B, first thing, TA, we don't know. Remember what we said. When you cut a spring, spring cut tension is 0. If you don't cut a spring, spring cut tension will be same. We never talked about a string. Strings can tension suddenly change depending on the scenario. So we don't know. It need not be the previous value. It's not a spring, it's a string. That's the first thing about a string. You see a string, the first thing you should say is I don't know. The tension in strings can change suddenly to anything. So we need to literally draw an FBD and check what is happening. So let's try and see. And what about TB? You are cutting TB, so TB will be 0. TC will remain 3mg. Agreed? Now let's draw the FBD. So first let's draw for 3m. Let's draw for m. So MA, the force is TB, which became 0. This is mg. This is TA. Now, if you think about it, the strings cannot push. TB is 0, right? So the block will try to fall down. And we know strings cannot push. Therefore, TA must be 0. This is what will happen. The moment the upper part is cut, the A block will try to come down. The string here will become loose like this. So TA becomes 0. That's the reason tension is 0 here. And the only force acting is mg. So this block will have a free fall, A is equal to G. Is that making sense? Because strings cannot push, so it will suddenly become loose. So tension in A becomes 0. You have to prove this. You cannot take the previous value. And then if you draw 2m ka FBD, this is TB, which became 0. Your own weight 2 mg. You have TC, which is 3 mg. So 5 mg is pulling down. So acceleration of 2m will be total weight 5 mg by 2m. That is 5g by 2. Whereas for 3m, tension TC is still 3 mg. Your weight is also 3 mg. So this will remain at rest. Got it? So m will fall with g down, 2m will fall with 5g by 2, c will remain at rest. Is this making sense, everyone? So be careful with that. You don't know what is the tension in the string. What about c? What happens if you cut it c? Try. I'll give you another minute. I hope you understood what will happen to the string. Now the story is the same again. When you cut it c, what is TA? I don't know. In this case, since TB is 0, there is no one to support you. The block has to fall down and the string cannot push. So string tension becomes 0. Show you? Same story. Now we are cutting at C. TA, we don't know. TB, this guy will remain same. TC will become 0. Now let's start from 3m. So 3m, this is TC 0. Your weight is 3 mg. There's no one to support. You'll have a free fall. For 2m, your tension TB is 5 mg. Your weight is 2 mg, and TC guy has become 0. You will just jump up. So that would be 5 mg minus 2 mg is equal to 2 ma. A is equal to 3g by 2. Now, if you draw the MK FBD, you are pulling up with TB, which is 5 mg, much greater than your weight, and your own weight is mg. So the block is trying to go up, but the string cannot break. It won't move. The force is higher on the upper side, isn't it? So technically speaking, the block will try to go up, but the string will not let it go up. Since the string cannot break or stretch, block remains at rest. And you can calculate here, therefore tension at A will be 4 mg. So whatever extra force you need, A will provide that and will keep the block at rest. So this will have acceleration 0. So the reason why M is not moving is a different reason only. The string is not letting you stretch, so you won't move. But in the previous problem, there is no upward force. The block is trying to come down. The string couldn't do anything. This is what I was saying. If it is about pulling, string will come and do everything. If it is about pushing, string will say, boss, I'm sorry, I can't do anything. And it just becomes 0. Are you getting the difference? So in this case, C will 3m will fall with G. This 2m will go with 3G by 2 and M will remain at rest. Is this clear, everyone? All clear with this? Any doubts on this? It's a pretty good one. You should definitely try this again on your own. This one case will cover literally everything that they can do with cutting of springs. So that is there. So that is a bit about springs. We still have a few more models, and then after that we have pseudo force. I think that we will do in the next class. We will discuss the paper now. So do make sure to go through this. We almost touched 54 problems. You will be able to do everything in NLM. You're doing my booklet, or you're doing from your PACE booklet, you're doing any material, whatever you're doing, finish it off. You can take a 1 week as a deadline, try to wind up this by next Wednesday or next Thursday. Next class, when we catch up, we are going to do pseudo force thing, and I think we'll start off with friction introduction at least. Now the chapters will go a little faster because the basics, right? Like I said, the free body diagrams and the constraints are the main ones. Once you know these two things, it is just a matter of putting forces, FBD equations